Welcome back, geometry students. Today we are going to do some operation of our vectors. So a couple things I want to remind you of from our last set of notes is when you see a vector, let me get my pen ready to go here. When you see a vector, it has what we call the initial point, and then the arrow is the terminal point. So one thing I want to remind you here is the initial point's here, the terminal point's here. And when we start to do operations with vectors, which means we're going to add, subtract, multiply, and such with those, that vectors actually hook onto each other. So when you initial the first one, where it ends is where the next one is going to start. So initial and terminal are going to be important as we work through our operation of vectors. And the other thing I want to kind of give you a reminder of, I shouldn't even say a reminder of something new here, is I'm going to ask you many times, what is the resulting vector or the resultant vector? It's not letting me. Resultant vector. And that's my final answer vector. So the answer is the resultant vector. So make sure as we go through this, you realize I'm going to use that term a lot, resultant vector. All right, we're going to attempt this. As you can see today, we're kind of back on not really a graph, but a grid. I'm going to do my best as I try to work with my stylus here on my iPad, but I can't promise it's going to be super good, so I hope you're listening carefully enough that you understand what I'm at least trying to do. So as we do operation of vectors here, you'll notice my first one and my second one, we're going to use what's called a scalar, or we're going to multiply by a vector. So the first one says 3 times the vector of rs, and rs is in those pointed parentheses 1, 4. So if you remember from our last set of notes, what that means is, and by the way, this is not a coordinate plane, so I can start anywhere I want on this. I'm using it just as a graph or a grid to kind of organize what I'm doing. So I'm going to just choose a point down here. I'm going to make it point R. And for this vector 1, 4, that means I'm going to go to the right 1 and up 4. And that's where I'm going to end, and my resultant vector there is rs right now, or I should say my initial vector is rs. So that's my first vector, rs, but it says 3 times that. So when I go to start my second of this same vector, I'm going to start where I ended. So now my starting point here is r prime, because it's my first change, and I'm going to go again over 1 up 4, and I get r prime s prime goes here. But that's only 2, so my third one is also going to start where this last one ended. So there's my r double prime. I'm going to go over 1, right 1 up 4. And here is my final s double prime here. So here is my movement here. Now, when I talk about my resultant vector is my answer. And it's super important to realize what that means is from where I started, where did I end? So if I look at this, where I started is over here on R, where I ended is S double prime, and I need to give my answer of what is my vector. Well, that one moved over 1, 2, 3, and I went up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So over 3 and up 12 is my resultant vector. Put my vector sign above there. And so my answer, or my resultant vector for this first question is r s double prime, and my answer is 3, 12. Notice the pointed parentheses. That tells somebody that I am working in vectors, and I'm not just finding an ordered pair. So don't put your regular parentheses, make sure they are pointed. So let's try our second one to the right here. It says 1/2 of vector xy, which is 8, 2. So let's start with our original, which is 8, 2. Again, just find a point to start with. That'll be my x. 8, 2 says go to the right, 8, 2, 3, 4, 5, 6, 7, 8, and up 2. So this is my initial, or my original. My initial point is x. My terminal point is, y. I don't know why I just wrote a z. And now I want to take half of that. So this one's a little bit different than the first one I did, but for half of that, I would just think, well, half of my movements was 1, 2, 3, 4, and up 1. So right here would be halfway. So this x and then my new y prime right there. So my new vector only goes from my initial spot to my ending point, so there's where it is. So my x, y prime will make it to the right 4 and up 1. All right, so let's go through now and let's start adding some vectors. Move my page up a little bit so I get more room. My first vector here is AB, and that's 2, 3. So once again, I find a spot on my grid to start with. Here's A. I'm going to go to the right 2 and up 3 for my B. Always putting an arrow on that terminal point so I know where I ended. Because now when I add CD to it, I'm going to start where I left off, okay? So I'll just keep it on green here. C is going to be exactly where the B was, and D is going to go, we're going to go from C, right 4 up 2. So here's my new one here, and there's my D. Now, when I go to find my answer, I want my resultant vector. So my resultant vector starts where I started and ends where I ended at the final. So this is my resultant vector. When you graph these, I do want you to always draw that resultant vector. So if I look, my new vector would start at A, and it ends at D. So there's the name of my new vector, and I need its movements or its component form. So I come here from A. Well, from A, I went to the right 1, 2, 3, 4, 5, 6, and I went up 1, 2, 3, 4, 5. So my resultant vector is 6, 5. All right, let's try GF plus JK here. And I do want you to notice that my GF starts at negative 5, 6. So if I started at this bottom left corner like I have been, I'm going to run off my page or off my grid, which isn't going to help me. So I'm thinking if I go left 5, up 6, and then I'm going to go right 3, down 7, I'm going to start kind of over here to the right instead. So I'm going to find this point here. Again, there's no right or wrong spot here, and I'm not even on a good point. There we go. At G, and I'm going to go left 5 and up 6. So here's my first one of GF. And now when I add JK to it, remember that I start where I ended, so my J is going to start right at the same spot. I'm going to go right 3 and down 7. It almost looks like I crisscrossed over there, but I only draw from first to last there. So there's my K down here at the bottom. And my resultant vector is from where I started to where I ended. So I started at G and I went to K. So GK is going to be my resultant vector. That's the name. I also draw that. And now I want the component form. So if I go from G to K, how far did I go? And remember, I always go left or right first. So it looks like I need to go to the left, and it's 2 to the left. So that's a negative 2 to show it's to the left. And then it looks like I go down 1, so minus 1. And my resultant vector is negative 2, negative 1. All right, so adding isn't too bad. Let's go ahead and try some subtraction here to end this. By the way, there were others. We're not going to graph all of these, but I just want you to have a visual so you know how to do some of these. All right, so on this first one, I have CD, which is 4, 6, and I'm going to subtract EF, which is 3, 2. So once again, I'm going to just find a corner to start in. So there's my C. I'm going to go to the right 4, up 6. And here's my first vector, CD. Now, I'm going to kind of draw something here so you can see it, and then I'm going to erase it. So kind of make sure that you kind of see what I'm doing and what I really want when this is done. I'm going to subtract 3, 2. Well, normally I would start at D and I would go right 3, and I'd go up 2, so it'd kind of go like this. That's the normal. But when I subtract, I'm actually taking that away. So I go opposite what I'm doing. So I would actually take away 3 to the left and go down 2. So my actual one, because I'm taking it away, is going this way, and that's my EF. Okay? Now, if that was confusing, I want to remind you of a rule that we used with subtraction before. If you remember, subtraction is add the opposite. We could rewrite this problem as 4, 6, changes to add the opposite, which would be negative 3, negative 2. Which is the same as moving left 3 down 2, which if you look at my graph, that's what I really did when I went from E to F, is I moved left 3 down 2. Okay, So my resultant vector here, let me change colors, is going to go from C to my ending point of F. So my resulting vector is CF, and I started and I went to the right 1, and I went up 1, 2, 3, 4. So my resultant vector is 1, 4. So let's do our last and final one on this graph, or grid, I should say. And we're going to start with LM, which is 3, 7. So I'm going to choose a point, make it my L. I'm going to go right 3, up 7. There's my LM. And now I'm going to subtract NO. Instead of subtract, I'm going to change it to add, and I'm going to make it the opposite. So that's going to become a positive 2 and a negative 1, which means my N, which starts right here where my arrow is going to go to the right 2 and down 1. So here's my subtracted value now of NO. Normally I would have gone left 2, up 1, but because I'm subtracting, it's opposite. And now I'm looking for my resultant vector. That's the one that results from my operation. So I go from L to O. So my resultant vector is LO. Oops, sorry, no bottom arrow there. And in component form, which is those pointed parentheses, it looks like I went to the right 1, 2, 3, 4, 5. And I'm going to go up 1, 2, 3, 4, 5, 6. So there's my resultant vector. Now, I know there's some of you that have been watching this going, I could have told you that answer without drawing. And I do understand that, and that's what we're going to do on the back of the page. But I do want you to be able to also draw these so you can have a visual of what happens when vectors work together, where one starts at the initial, has a terminal, and the next one needs to start at the exact same place where the terminal of the last one was. So I do want you to be able to visualize these and to be able to draw those. So let's go to page 2. On page 2 here, you'll notice I didn't put any of these grids because we're going to do these without the grids. So at the top of the page, you'll notice that I have a box of rules, of equations, however you want to look at this, kind of like a theorem if this was in a book. And it tells us if we have two vectors, what will happen. Well, the first one they call is K being a scalar, and that's kind of like our multiplication. It just means multiply both the numbers inside the vector by that number. If I do A plus B, that's telling me to add the first two together and then add the second two together. So you're adding the horizontal components first. Those are your left and rights. And then your vertical components second. Those are your up and downs. And then if we subtract, we're going to subtract our first two and then subtract our last two. So let's go ahead and practice this so you can see these. And again, when you go to do these, show as much work as you need. I'm going to show a lot of work so those that are watching know what I'm doing. So my vectors are named a little bit different this time around, so I'm not going to be able to name my resultant vectors here. Notice I just gave you 3 vectors, x, y, and z. So the first one I have 3 times y. So this is a scalar. It means I'm going to do 3 times my vector of y, which is -4, -6. This means I'm going to take 3 times my x coordinate, or I shouldn't even call it the x coordinate, my horizontal movement, and then I'm going to do 3 times my vertical movement. So 3 times -4 is -12, and 3 times -6 is -18. So my resultant vector is -12, -18. And that's like the first one we drew when we drew it 3 times on top of each other, kind of. But this time we just do the math and we skip the picture. All right, let's go to my second one here. So I have half of my y. So this is kind of like the second one we did do. So if I go half, I'm still using that same vector of -4, -6. No matter what the scalar is, a fraction, a whole number, whatever, it still multiplies times each component. So I have 1/2 times my -4. And I'm also going to do 1/2 times my -6. So 1/2 of -4 is -2. 1/2 of -6 is -3. And my new resultant vector is -2, -3. So that's the same scalar as we drew on our first 2 grids. So let's go ahead and do some addition. Change my color here. I'm going to try to keep it so that you can tell which problem is which here. So now I'm going to do a little addition, okay? So x was 3, 7. and vector y is -4, -6, and I'm going to add together. So when I add, first I'm going to add the horizontal component. So I'm going to do 3 plus my -4. And then I'm going to add my vertical components, which is 7 plus my -6. So 3 plus -4 is -1. 7 plus -6 is 1. And my resultant vector is -1, 1. So moving on here, we'll try my next one, y plus z. So y is -4, -6. And I'm going to add to it z, which is 6, -9. So again, we're going to add those horizontal components, the first two together first, -4 plus 6. And then I'm going to add my vertical components, my second two, -6 plus -9. -4 plus 6, my horizontal components gives me 2. -6 plus -9 gives me -15. And there's my resultant vector. All right, moving on to some subtraction. Now, addition, I didn't say anything about the order, but subtraction, it's super important that you keep your order the same. So on my first one, I have z minus x. So z is 6 minus the 6, -9, and I'm going to subtract x, which is 3, 7. So just like with addition, I'm going to take those two horizontal components first. This time I'm just going to subtract them. So I have 6 minus 3. And then I'm going to work with the two back ones, which are my vertical components. So -9 minus 7. And I can go ahead and do the operation. 6 minus 3 is 3. -9 minus 7 is -16. And there's my resultant vector. Now you'll notice as I go to my next one, it looks almost like the same problem, but the order is different. I'm going to do x minus z. Does it make a difference in my order? So let's try it. X is 3, 7, and I'm going to subtract z, which is 6, -9. So again, starting with my horizontal, I'm going to do 3 minus 6, and starting with my vertical, I'm going to do the 7 minus -9. Make sure we get both of those subtraction and the negative in there. So 3 minus 6 on my horizontals is -3. 7 minus -9. Remember, when we have minus and negative, we add the opposite, so that'll become positive 16. And I get the answer of -3, 16. When I think about and I compare these two answers, if I look at 3, -16 here, remember, that would have gone to the right 3 and down 16. When I look at -3 and 16, that would go left 3 and up 16. So we're definitely going in completely opposite directions, okay? So it does make a difference what order we do these in. All right, we have 2 more examples to go. So let's move our paper up here. And you'll notice I'm mixing all kinds of things here. I've got a scalar with an addition, some division going on here. So let's work and practice through these. All right, changing my pen color. So the first one I have is 2x plus y. So that means I'm going to go 2 times my x, which is 3, 7. Oops, should keep that point in parentheses there. Plus my z, which is 6, -9. Okay, so first I'm going to do my scalar. So that means I'm going to go 2 times 3 and 2 times 7. So that gives me the new vector of 6, 14. And then I'm going to add it to my 6, -9. So again, joining those horizontals first, I'm going to skip a little bit of my work here, or not showing it. 6 plus 6 there gives me a 12. And then the verticals, 14 plus -9 will make 5. And I get a resultant vector of 12, 5. All right, last and final one for today. I'm going to have a mixture here. I have a scalar of 3 times my x, which is that 3, 7, minus my y, which is -4, -6. And you'll notice I have a great big division bar with a 2 underneath. So the first thing I'm going to do is this one right here where I'm going to multiply. I'm going to skip a little work again and just multiply here. 3 times 3 gives me 9. 3 times 7 gives me 21. I get a new resultant vector. And I set it up with my subtraction. And don't forget I have this big divide by 2. So across the top, I'm subtracting. Again, I'm not going to show on my work, but kind of follow me here. I have 9 minus a negative 4. Well, minus a negative becomes positive. So I get 9 plus 4, I get 13. 21 minus a negative 6. That's my horizontal 21 minus, my vertical 21 minus a negative 6 makes 27. And I'm going to still have this 2 on the bottom. All right, so right now I have a vector of 1327 and I have a divide by 2. I can also think of that as 1/2 of 1327 times 27 vector. And that's a scalar, and I can go ahead and distribute that through. We have two options. You can make them decimals, you can make them fractions. I'm just going to leave it 13 over 2 and 27 over 2. And there's my final and resultant vector on that one. And that's our vector operation notes. So you have a worksheet, vector worksheet number 2, that I would like you to practice on. Just a heads up on that worksheet, it actually contains a lot of practice from our vector introduction notes as well. So if you're not sure how to do something, go back to the earlier notes and it will help you to name them, to write their component forms and such like that. So go ahead and practice. Once again, email me if you have any questions, or go ahead and send a question on the stream so all the students can see it. Good luck.